Consider two statically charged balloons that repel each other. Tie the two balloons together. What do you suppose happens? They'll want to stay as far away from each other as possible. For just two balloons, that means they'll be 180 degrees apart. We call this a linear geometry. Now, add a third statically charged balloon, and what then? Well, the three balloons will want to be as far apart from each other as possible. The result here is that the balloons will space themselves apart by 120 degrees. You'll also see that the balloons lie within a plane. So to be as far apart from each other, they naturally lie 120 degrees from each other within a plane. We call this a trigonal planar geometry. What about four balloons? To be as far apart as possible, the result is what we call a tetrahedral geometry. The tips of each balloon spell out the corners of a tetrahedron. Tetra means four, hedron means face. So a tetrahedron has four faces. It's what you get when you pinch some bread dough with your fingers, a tetrahedron. It looks like a pyramid, but with a triangle at its base. Here's the deal. Electron pairs behave exactly like statically charged balloons. Try putting them together, and they'll do their best to stay away from each other. Two pairs will result in a linear geometry. Three pairs, a trigonal planar geometry. And four pairs, that results in a tetrahedral geometry. Let's look at some examples. Here's beryllium hydride, BeH2. Notice there are two pairs of electrons around the central beryllium atom. The last thing those electron pairs want to do is congregate to the same side of the beryllium atom. Nope, that's not happening. Because the electron pairs repel each other and want to be as far apart from each other as possible, what you end up with is a linear geometry. Here's aluminum hydride, AlH3. Notice there are three pairs of electrons around the central aluminum atom. To optimize separation, the pairs space themselves 120 degrees apart within a plane. The result is that trigonal planar geometry. Lastly, consider methane, CH4. With four electron pairs, the result is a tetrahedral geometry. Make sense? Okay, now let's push the envelope a little bit by taking a look at our dear friend, the water molecule. How many electron pairs do you see around that central oxygen atom? Let's count. 1, 2, 3, 4. Great. What you see is that two of these pairs are caught up in a covalent bond between the oxygen and the hydrogen. The other two pairs are what we call non-bonding electron pairs, also known as lone pairs. Bonding pair or lone pair doesn't matter. What you've got here are four electron pairs. Now take a wild guess as to the geometry that results when you've got four electron pairs trying to surround the same atom. Will they all bunch to one side? No way. Will they separate by 90 degrees within a flat plane? Well, that's better than bunching to one side, but there's an even better solution when you look into 3 dimensions. They'll pucker up into the tetrahedron, where the angles between them are about 109 degrees, which is greater than the flat 90 degrees. So a water molecule has a tetrahedral geometry, just like the four balloons. Make sense? But when we look at the water molecule, we're mostly interested in where the atoms are, the hydrogen, the oxygen, and the other hydrogen, H2O. How are these atoms oriented to each other? What's the shape? For a moment, ignore the lone pairs. Focus only on the atoms. What you'll see then we call the molecular shape. The molecular shape of water is bent. There's this distinct angle between these three atoms of about 109 degrees. So why aren't the two hydrogen atoms 180 degrees apart from each other? It's those pesky lone pairs that prevent this from happening. With the 4 electron pairs around the oxygen, you necessarily have a tetrahedral geometry. But when it comes to the shape of the molecule, you've got a molecule that looks like it's bent. To drive this idea home, check out the ammonia molecule, NH3. It has 4 electron pairs around the nitrogen. Thus, you get the expected tetrahedral geometry. But what's the shape of the molecule? Just ignore the lone pair. There's no atom there. It's just a lone pair of electrons. Focus only on the atoms, and what you see is this. Call it what you want. Most chemists describe it as a trigonal pyramid. Here's an algorithm that you can use to suss out what's what. Step 1, count the number of electron pairs. This will give you the geometry. Then count the number of atoms surrounding your central atom. This will give you the shape. Let's look at hydrogen fluoride. There are 4 electron pairs around the fluorine. That means a tetrahedral geometry. But there's only 1 atom coming off of the fluorine. So the shape of hydrogen fluoride, is linear. To wrap up, electron pairs, be they bonding or non-bonding, repel each other and want to be as far apart as possible. This results in a particular geometry. It's from this geometry that you're but one step from figuring out the molecule's shape, which you get by focusing only on its atoms. That's good chemistry. Good chemistry to you.